Also, ich spreche dann auch, wir haben wirklich an, wenn ich nicht Lösungen
The talk I want to do is not a formal system to evaluate numerical errors. It's more a hands-on approach, and it is a result of our project. So we were with the Center of Excellence for Global System Science. This is one of the HPC centers that have been funded by the European Commission to push the application of HPC in newer fields, and one of these newer fields is global system science. This is quite a new area that is concerned with the modeling of complex scientific and social problems, so like banking system, health system, urbanizations or infrastructure planning, things like that. And the idea was to work with agent-based modeling systems and let them run on HPC machines. So very simple agents with a matrix, with a pattern to behave that get their input from the other agents, and then the system evolves and you could set up a model in a very simple way and then look what it does. So what is, how does the next Ebola spread or something like that. So what we did in this project was, our task was to look for numerical algorithms that might be used in the modeling thing, and look what the numerical errors. So because if you think of these agent-based modeling systems of a lot of time steps, then the question is, would there accumulate a lot of numerical errors? What we did in the concrete case is we implemented a library, an interval arithmetic library in Haskell, and then we used this library to validate one specific algorithm that came from the project. The outline of the talk is therefore with something say about the floating point arithmetic itself, so its flaws, if you say so, then about the approach of interval mathematics, how we did the implementation, and then something shortly about this algorithm and its validation and the outcome results. So floating point arithmetic, everyone knows well, and everyone tries to forget immediately about what we learned about these final representations of real numbers, which is not really a representation of real numbers, but something that is the best we have. As we all know, the number, the set of floats is not a field, which means the arithmetic is neither correct. So if you divide two floating point numbers by each other, then the result is a floating point number, yes, but it's not necessarily the one that is the real number you wanted to represent. It's not associative. That means if you implement an algorithm, you have to be very careful with the sequence of operations. The rounding errors may accumulate, this is known, and on the other hand, there are well-developed methods in numerics to analyze how this specific algorithm you are considering will behave, but this is very costly and you need a lot of time to make a proper evaluation of some new algorithm. So, and it depends whether it's worth to analyze an algorithm. So we had another idea. We wanted to use interval arithmetics for this purpose. And this is also not a new approach. Interval mathematics is known, I think, at least 40 years or so. The trick is that instead of using real values, you could also use intervals, and then you calculate not the real-valued functions, but instead interval extension of this function. It means you wrap your function values inside intervals, and the idea is that the real value you are interested in, and you don't know exactly which one it is, because interval arithmetic can also be used for propagating uncertainty. The compositional or computation rules you need, they have to ensure that the real value is also contained in the result. The arithmetic states this this property that the real result has to be contained in the result in this with this conclusion property. If we have some operation like the arithmetic operations, then we want to ensure that the result here should be an interval, and so this op and this op have different types, of course. So this is the one for the intervals, and that is the one on the real numbers. And we have to ensure that every possible outcome from arguments from the first and elements from the second will be in the result. So this is for the arithmetic operations. One problem here is, as in the real calculus as well, that we have to ensure that we don't divide by 0, because there's no rational solution for that. If we define operations like that, then we can deduce this monotony property, which is very useful when you think about refinement, because inclusion of one interval in another can be read as a refinement. And of course, we are interested in tight intervals. So it's not the purpose to make the intervals as big as we can, but it's the opposite. We try to confine the intervals as small as we could get them. So this definition ensures this monotony. If you have a refinement of x prime and refinement of y prime, then the operation is so the result of the refinement is also a refinement of the other one. Beside the case 0 case is this calculus of intervals over real numbers algebraically closed. The special case of dividing by intervals containing 0, this is to be read for real numbers here, and this is the table comes from the proposal for the ICFP standard for intervals, the 1788, which is now released, I think, in 2015, and it shows how to handle the intervals. The purpose why I have this table here is to illustrate what happens when the 0 is in the middle of the interval you are examining. And then the problem occurs here that the result, so what you are doing is clear. You pick the smallest number, so in floats this makes sense, in real numbers of course not. So for reals, you read it as you split up the interval into the part close to 0, and you start with a very small epsilon after 0, and you perform 2 division operations, and what you get in the end is also not an interval. This is no longer an interval, but it is 2 intervals. So if you want to work with interval arithmetic in a closed calculus, then either you have to ensure that this case doesn't occur, or you have to lift all the things to lists of intervals, which would give a closed calculus. So that fortunately this was not our problem, because in our algorithm the intervals we had to divide by were strictly positive. So it didn't came to a problem. So now the interval arithmetic, how it is done, it's clear. this is with the idea that the operations have to be defined in that way. We can see that the very natural definition for the plus is take the lower bounds and add them, take the upper bounds and add them, and that's it. A little bit more complicated is the product, because you have then to build every pair of boundaries, so the left bound of the first and the left bound of the second, and so on. And then you take from all these products the minimum. This will give you the lower bound of your product of intervals, and the maximum. This will give you the upper bound of your product. This is for real numbers. If we want to implement it, then we have to take care what we do with the tiny bits where a real number is not representable by a float. And that means we have to perform here some rounding operations. So this has to be done on the CPU. This is the plus from the ICFP standard for float. And afterwards we have to perform a downwards rounding to be sure that we have everything that could possibly be as a result in the resulting number. And here on the other hand we have to perform the plus with the upwards rounding. What we did, we started with the implementation of the data type interval, and then we used Haskell because Haskell accepts this standard, and that means we have access to the, some constants and functions that are required by the standard. The problem that occurred was that we had to deal somehow with these rounding modes. So Haskell allows to set the rounding mode, but the problem here is switching rounding modes is costly. So if you want to perform a lot of interval operations and every time you have to stop the CPU to switch the rounding mode because this is a flag on the CPU, that's not a very good idea. We were thinking about these things, so we had this HPC sender, so one of the ideas was to parallelize and perform the downwards rounding on one machine, on one CPU, and the upwards on the other one. But then I came across an interesting paper that seemed to address exactly the problem I had. And the trick is, this is a paper published in 2015. They gave a way to simulate the arithmetic operations with fixed rounding mode. So the rounding mode is set in a fixed way, so it's rounding to the nearest, which is anyway the default rounding mode in Haskell, and it uses only constants and functions that should be available in Haskell because it sets the ICFP standard for floats. So, and that's where we start. This is the epsilon is the distance from one to the next smaller float, so from the normal to the subnormal. Min-normal is the smallest. This is what formerly in the table was called the epsilon. It's now the min-normal. This is the eta is the min, the smallest positive subnormal float. And then we implemented for every arithmetic operations on doubles. So because we worked on double precision, one version with downwards rounding, so that simulated downwards rounding, and one version with upwards rounding, according to the results from the paper from Ram and the others. So now we had for the addition, and we did likewise for the multiplication. For the multiplication, a little bit of stress because we used the maximum function and some strange things happen there because this is not symmetric. that was quite new for me. We implemented then the max IEEE function that solves the problem, because this is the one that is required by the standard, and the standard doesn't do the job properly. I think that has to do with monotonicity properties and the comparing of NIN with other numbers, but it was a funny joke to why it didn't behave like we expected. So it was such a simple thing. So now, with all so what we did here is the library contains the data type interval, interfaces to extract the boundaries. We have a way to measure the width of the interval. Then we implemented a couple of expressions, so interval valued function expressions that at the current state are not in every case the proper interval extension function. They work for training and test purposes, but we have to improve them. But at least there is a library available that has arithmetic functions, so like square root, exponential, polynomials, and things like that. And then with this library, we started to validate one of the procedures that have been used in the project. So now I have to explain a little bit what the purpose of this procedure was. As I said before, the pilots in the project wanted to use Asian-based modeling systems, and they wanted to forecast the development of buying green cars or something like that. And using Asian-based modeling system means you need data about Asians. And then this is also something that I learned in the project. Getting data is a very hard job. So there are a lot of data sources, open data sources, where you can get statistical data, but it's not as you would like to have a full set of agents with every property you are interested in. So the health status, the income, how the housing properties are, the status of family and things like that, so you don't get this kind of data. What you do get is marginal distributions for some of these properties, and if you're lucky, you can also have a small sample of people that have participated in some special study or something like that. So small sample means 1,000 to 30,000, so like in pharmaceutical studies. Then you have a full set of information about one agent, so more than, I think, 30 properties or things like that. So, and these two things combine, the marginal data and those microsample. There is an algorithm, and the most prominent of them is the iterative proportional fitting, that glues both of these information together and produces in the end a synthetic population. That means a data set of agents equipped with the properties you are interested in. So it's very hard to explain the n-dimensional, and therefore I will do only the two-dimensional iterative proportional fitting. So you assume that you have two properties that you want to observe, so that may be age and income, and then for each of the properties you have classes, so like income from 0 to 10,000, from 10,000 to 20,000, and so you have several, this is the K number of classes of the first property, and the L is the ages, then you have the number of classes for ages, so 0 to 5, 5 to 10, and so on. And then you have this microsample that gives you for every of these classes a number of people that have both of the conditions that meet at this point. And you get from another source, usually you have another source, marginals. These are then vectors that have the right length. For each of the classes, you have the number of people in your population like Europe, Germany, US, or something like that have the required properties. Yeah. So, and then of course this doesn't fit because the microsample in each column doesn't sum up to the number you have here, only by luck. And the trick is now you have this microsample, you have the marginals, and then you perform a number of adapting steps until you reach a point where you cannot see any more improvement. The result is then a least square fit for the distribution in V. The algorithm itself was invented in the 40s, but has been recently reused for these purposes here. And there is a new proof for convergency that has been published in 2013, because this was the problem we had. If you calculate something on the machine, it doesn't make sense to speak about convergency. What we want to have is kind of fixed point, which is not the same, or we want to have a good estimate, but we don't have any control, and therefore I have been looking into this proof to find out what are the conditions that the matrix you are developing will go into the right direction. This is an example. I think we should skip that. It's just to illustrate what the algorithm does. These are the marginals. So this is the vector that was called R. This is the vector that was called S before. Both of these vectors have to sum up to the same number because they are properties of the same population. And this is the smaller measures. This is what I call the microsample. So now in the end we want to have here a matrix that keeps the dependencies that you have in the microsample, but adds up in each column and line to the marginals here. So, and then the first step is you adapt the lines. That means you sum up all the entries in the line, divide your first entry by this, and then multiply the row sum. You do so with the whole line and with the second line as well. And after the adaptation of the row comes an adaptation of the column. And you proceed, and usually it's done in a way that if you measure the differences between the two matrices with the least square measure somehow matrix, and if that doesn't happen much anymore, then you stop the process for your conversions. You don't have any control. What we did, we implemented the algorithm in Haskell. What we use is for the purpose, we defined the data type IDF. Num is what we call it to go back from this divided by intervals containing 0, because we wanted closed calculus for intervals, and if you go back here, this dividing by 0 would only occur if the row sum would be 0, which is pointless, then you would leave out that. So it doesn't occur. And this is the simple diff, is the division that yields in every case one interval and not a pair of intervals. We implemented procedures for this adapting rows, adapting column, made the recursive definition, and we made, for control purposes, the number of steps an explicit input. So no fixed point procedure, but we call it with a certain number of steps. And after this, we did the same for the n-dimensional. So if you want to have more than 2 properties for your agents, but you want to have n properties, for instance, that we would need an n-dimensional IPF. But I must say, at this point, so IPF is exponential in the number of parameters, as you would guess, and we try to run it on more than 7 parameters, and we get stuck because our random sample production suite, it took too long to produce the samples. So we have no results beyond for n more than 7. So how did we do the validation? So one lucky situation with the IPF is that we have a control instance for the IPF, because we can check if the rows sum up to the marginal or if the columns sum up to the marginal on the right side. Because we do, so there's a series, we do either the rows or the column first, and we check then for the other. Doing the columns, make the column sums right, but destroys the row sums. So if you want to measure how good your algorithm performs, then you measure the other one. And that's what we did. So we started the IPF with singleton intervals as entries, and then we used the interval arithmetic to track down the numerical issues. That means we have the left bounds of the matrix. This means n times the adapt row, adapt call procedure applied to this matrix, and we have the right bound, and then we have also to, because the deviations were really small, we measured the relative error. And that's the result. It's a nice picture, very colorful. What you see here, the x-axis is clear, it's the number of iterations. This is for only one sample, but we did a lot of samples. I think it was about 200 for every dimension or so. And the picture was always the same. The color, each color is for one column, that because the entries in the column could deviate a lot from each other. So if you imagine that you have files, so from 0 to 5 years old, and the income is probably very small in this area, and for elder people you might have a better distribution of income than for the child. So the columns could really different from each other. So therefore we measured them. What you see here is, at the very beginning, it's clear that the deviation is quite big in the first step, but then you also see that it converges to some small value. This is a logarithmic scale, because otherwise it would not have been possible to show it at all. And then the imprecision of the interval. So what you see here is both of, and this is also the case for the other colors, both of the left bound and the right bound that split up. So you have the one of the bounds, so the left bound goes beyond the marginal sum, and the right bound goes, one is lower than and the other one is greater than the bound. And then after these 6 or 7 steps, so it depends on the dimension how much you need, the errors that come from this safe rounding mode will take the whole thing apart. So it doesn't make sense to run more than 6 iterations, because afterwards the numerical errors increase. What we don't know at this point in time, whether this is an artifact that comes from the interval arithmetic, or whether it's really the problem that comes from numerical errors. So the conclusion, what we did in the end, and this is the proof of concept we made, we implement the algorithm we are interested in with a type class that allows the types that we really want to compute on and allows the intervals. So it's one implementation that fits the real application and the validation purposes. At the same time, the interpretation of the result is small intervals mean that you have only a few numerical errors. The opposite, of course, is not true. If the intervals are bigger, then we don't know what the cost is for these bigger intervals. That might be a problem with the algorithm. It might be a problem with the interval arithmetic itself. Or it might be this over-approximation that comes with interval arithmetic. So there are tricks to solve this, but if you have intervals, then you can continue developing the algorithm throughout a good way. That's the good message here. That's the behavior I just explained. What I do think is that this approach is suitable for first analysis when you are developing an algorithm or a program and you want to observe how the different the lack of associativity brings you to, you have to choose which of the operations you do first. And this could help to decide which of the operations should be first and which should be performed second. And especially in cases where it is not worth to perform a thorough numerical analysis on paper and things like that, where it would be way too costly just to see what happens with your algorithm. That's a good choice to perform it in that way. So this is the literature. For those who are interested, that's a very interesting paper about the interval with fixed rounding mode. This is the original article about this ICFP algorithm, as you see, from the 1940s. And this is the quite recent new proof about the convergency of iterative proportional filtering. So that's it. Thank you.
Is your code available on GitHub or somewhere?
Yes, it is. At the moment, it is available under Name HZJ, but will be when, so we have to include, it is available. I could write you down the address, so the GitHub account. It will be available under the projects. So the project has also a GitHub repository, and then if we have, so we have to include the license things into the code, and that's the missing output. But it's available, it's full function. Yes.
Okay. Thank you very much, Eva.